So in this quick video, we are going to talk about forecasting errors and specifically how can we measure forecasting errors. Remember the first law of forecast that our forecasts are always wrong. And so we're trying to be less wrong. And so we need a quantitative way to do that. And in other words, we want to minimize some measure of forecast error when we're creating our time series forecast. So just to remind and kind of get associated with some notation, if we think of a given period T and we have demand that occurs, that's D of T, we forecasted that F of T would happen. The difference between that would be what's sometimes known as a forecast error in a given period T. Typically, we care about a time series. So that's a collection of data, collection of D of T's. And so we typically have forecasting errors that consider all of those observations. And so some common forecasting error measures, one that's common is sometimes known as MAD, or the mean absolute deviation. So that just takes what we thought was going to happen minus what actually happened, take the absolute value of that, and then it's the average over that absolute value. Another common forecasting error measure is what's called MSE, or mean squared error. So now instead of taking the linear difference, we're going to take what we expected minus what happened and square it, and then take the mean of those squared terms. Sometimes we don't necessarily care about the mean. We want the sum of squared errors. And as we'll see in R, the package that we use, SSE will show up. And so this is related directly to MSE in the sense that it just doesn't have 1 over n. Okay. There's also something called the mean absolute squared difference. Sorry, that's repeating again. The mean absolute percent error. Here, all I'm doing is trying to figure out if I'm off by 10, is that a really big deal or is that not a big deal? If my average demand is 1 million, being off by 10 is pretty great. But if my average demand is like 3 and I'm off by 10, then that's a bad thing. So MAPE just gives you kind of a relative measure compared to my average demand point, how bad are we? And then there's a thing called cumulative forecast bias, which in some ways is the simplest one out of these and just sums over your observations. How much was I off in a cumulative sense? And then sometimes there's what's called a tracking signal, which is the bias divided by the MAD. Okay, so these are all different measures of forecast error. And now we're going to kind of think about them and try to figure out, when are certain errors measures useful? What do if we're trying to minimize one of these, we may set different parameters in our forecast. What's the influence of that? So my first one I want you to think about is this thought question. So do you think the following statement is true or false? So if your forecast produces a cumulative forecast error of 0, and I provided the equation on the screen, then your forecasted demand must match your actual demand exactly in every observed period T. Do you think that's true or do you think that's false? So in other words, I got a bias of 0. Did I have a perfect forecast every single observation? The correct answer here is that this is false. You can get a cumulative forecasting error of 0 by having a terrible forecast in individual time periods. An example of that is in time period 1, I'm off by 1 million in the positive direction. But in time period 2, I'm off by 1 million in the negative direction. And therefore my bias, my cumulative forecast error is 0, but I'm off by a lot in individual periods. Okay? And so this is exactly why in all of those measures I gave you, we're doing things like taking the absolute value or squaring it. So we don't get this idea that we can be off in one period and off if it's the same in the opposite directions. They are no longer allowed to cancel each other out. And so sometimes this cumulative forecasting error is used. It's oftentimes used in marketing or sales where it doesn't necessarily matter day to day. I just need to meet my sales target over like a yearly time frame. So in those cases, you kind of want the cumulative measure. But in operations, which is what we're talking about in supply chains, if I'm expecting a lot of people to show up today and I have a staff of a lot of people and no one shows up, that's really bad. And then the next day, the opposite, if I have no one on staff or a small staff and way more people than I expect to show up, that's just bad performance. And so from a supply chain perspective, which we're doing much more operational decisions, cumulative forecasting error is usually a really bad idea. Instead, what is more common is companies to use either MAD or MSE. And so both of those equations are provided here. And you can see with these equations, we don't run into that problem. If I'm off by 1 million in one direction and off by 1 million in the other direction, I'm just off by 2 million in the MAD, right? Because I'm taking the absolute value. So on average, I would still have 1 million that I'm off each time period. Similar with the squared, we don't get that because a squared function is always positive, and so they don't get to cancel each other out. So that's why these are really common ways to think about time series forecasting for demand planning for supply chains. So my next thought question is, given these are both common ways, they don't have this problem that we saw with the bias measure, which one, which is the following is true? So forecasts that are periodically off by a lot will result in what? So what do I mean, first of all, periodically off by a lot? Let's say we have 100 data points, our N is 100. And in one case, we have one that's like every day I'm off by 1. Okay, so I forecast it 1 wrong. Okay, versus another data set, which it says I'm perfect, perfect, perfect. That next day I'm off by 100. Perfect, perfect, perfect. That's what I mean by periodically off by a lot. So in that case, which of the following relationship fits? Does MAD equal MSE? Does MAD less than or equal to MSE? Or MAD greater than or equal to MSE? Please pause the video, think about this, think about mathematically what's going on. So hopefully you came to the conclusion that the correct answer is B. And so let's just think about my example of if I'm off by 1, 1 squared is still 1. If I'm off by 100 squared is way more than the sum of those things. And so what does MSE do? MSE basically punishes our forecast for being off by a lot. We'd rather be off by just a little cumulatively than pretty good way off, okay? And again, it matters what are you using this forecast for, but if you're using this forecast for something like planning production amounts or staffing your employees, or a lot of the things that we saw in the Walt Disney example when they were staffing and using kind of this more granular forecast, it would be really bad for customer experience if I was off by 300 people in the 15 minutes versus just every 15 minutes I'm off by a couple, right? Why? Because usually there's what's called buffers, and we'll learn more about that in the next module, that we buffer against variability. So if I'm, I thought today there would be 30 people that show up this hour, instead there's 29. It's probably, something you can buffer in here or there. You're a little quicker, a little slower, not a big deal. But if I'm like, oh, I thought 30 people and 300 people showed up, everyone's waiting in line, you're not prepared for that, right? So because of this, it's quite common that we actually use MSE, is that we want to punish being off by a lot periodically. That really messes up our operation. So we'll see in most of what we do in this class, we will set our forecasting parameters using MSE, or using sum of squared errors, which is related to MSE. All right, my next thought question is thinking about how am I actually able to calculate these forecast errors? So my question here is, when are you able to calculate a forecast error measure in period T? So here's some examples of those measures. Is the correct answer A, before the demand occurs in period T? So that's D of T. Or after the demand occurs in period T? So do we need the demand to occur, or can we do it before that? So the correct answer to this one is also B. We can't calculate how well we did until demand happened. Okay? So we need the past to evaluate how good was our forecast. Okay? This is something that makes sense kind of obviously in these equations, but actually is a fundamental thing about what we'll spend a bunch of time doing when we go and actually implement this. We will be spending a bunch of time creating forecasts for period T when T is already in the past. You may be like, why am I forecasting the past? The reason we forecast the past is because the only way we can actually figure out how good our forecast is if we have historical data. And so we spend time forecasting the past so that we can, basically set our parameters, our alpha, beta, gamma, or move how many periods and moving average that minimizes one of these error rates. And in order to do that, we need a forecast for the past. And this will become more apparent when we get into the details of this, but I think this is a really important thing that sometimes when I first started teaching this, I kind of glossed over. And so we will spend a crazy amount of time forecasting the past. And that is for a purpose. That purpose is we can't calculate an error measure without forecasting the past. And we need an error measure to basically set our parameter values. This is also why if you've done anything in data science, machine learning, oftentimes what you'll see is you'll have a training and a testing data set. So what does that mean? We have a historical data set and we break it up into two sets. The first is what's called a training set, and that's what we use to build up our model. So in this class, when we're talking about forecasting, we will use that to figure out how should we set N, alpha, beta, gamma, which we'll talk about in future lectures. And we will do that by minimizing, say, MSE. So we need historical data to calculate MSE, but if I change this lever on my forecast, that will change what value of MSE I get. And I want to pick the correct settings that minimizes the difference between what I forecasted and what actually happened. Okay, so that would be how we get like N, alpha, beta, gamma. Once we have them and we set them by minimizing some error, we then go and see how well did it work. And so we use this on a whole different data set. It's still the past, but it's sometimes called a test or validation set. And it basically says, okay, I have my forecast created. I know my values for these input parameters. Now let me see how well it does on, observed data. And so, why do we do that? Well, one reason is it says, okay, is there some validation? If I actually use this in the future, how well do you think it'll go? It also prevents from what's sometimes called overfitting. If you use just the same data set, you might think it's going to do better than it actually does in the future. And this is really good for comparing multiple methods and choosing the best one out of that. And so in this class, we won't study a ton of methods, but realize there are a lot of these methods, right? So if you're at a company that's trying to build a forecasting model, you may try different types of forecasting models. You use the training set to build your forecasting model, which basically that means setting different parameters. And then you go test all of these different applicable models and say which one does best on your testing or validation set. And these are explicitly excluded from that. These two sets are known as disjoint. They're not, they're non-overlapping sets. And why do we do this? It allows us to evaluate forecasting methods kind of in a fair way and then recommend an approach. So that's the end of this lecture B2. And so in terms of the exam, these are the things you should be expected to know how to do. And what we'll talk about in the next lecture is, okay, let's actually go do this. So let's implement some specific time series forecasting methods, and we'll use R and some packages in R to do that.